So in this video, we're going to be discussing signal energy effects. So what happens if we have a function or signal and we have a sign change or a time shift, or even we double or alter the amplitude or magnitude in some way. So basically what we're trying to find out is what are the effects on the energy of the signal once we make these changes to the signal. So let's say we have some function f of t equals 3 times sine of t. And t exists from 0 to 2 pi. Just going to make it nice and simple. And I imported a graph to visualize f of t here. And we have f of t versus t. And this is 3 sine of t. We're going from 0 to 2 pi. So here we're going to be demonstrating a sign change on f of t. So let's say we have some new function g of t, and that's the negative of f of t, which means it's negative 3 sine of t. So thinking about this for a second, if we have some sign change and we're still looking for the energy of our signal, do you think that the energy is going to change? Because when we're measuring the energy, all we're doing is measuring the essentially height and width of the signal. So if we flip the signal or invert it or take the negative of it, we're not really altering the height or length. We're keeping the exact same height and length. We're just flipping everything. So I sketched g of t on the same graph that f of t is on. And so if we want to calculate the energy of g of t, we're going to take the integral over which g exists from 0 to 2 pi, and it's going to be g of t squared. So negative 3 sine of t squared with respect to t. And that equals the integral from 0 to 2 pi. Negative 3 squared is 9. We can pull that out of the integral later. Times sine squared of t dt. Then this is equal to 9 times the integral from 0 to 2 pi of sine squared of t. Now, for the interest of time, I just integrated sine squared of t. I'm not going to go through that entire mathematic process, but it's just 9 times 1/2 times the quantity x minus sine of x cosine of x, and that's being evaluated from 0 to 2 pi. We have 9/2 times the quantity 2 pi minus sine of 2 pi times cosine of 2 pi, which is 0, minus 0 minus sine of 0 times cosine of 0, which is 0. So we have 9 over 2 times 2 pi. And this is just going to be equal to 9 pi since our 2's cancel. And again, this is the energy of g of t, which is sketched in blue here. So now to make a comparison of the energy of g of t to the energy of f of t, we have to know what the energy of f of t is. So let's find that here. We can say that the energy of f of t is equal to the integral from 0 to 2 pi of 3 sine of t squared with respect to t. This is equal to 9 times 0 to 2 pi of sine squared of t with respect to t. And you'll see that, well, this is the exact same integral that we use to evaluate the energy of g of t, because of our squared functionality within the energy equation. No matter what the amplitude is, it's going to be the amplitude of the signal squared. So if we have negative 3 squared or 3 squared, it's both going to be 9, positive 9. So now you can see, no matter if we have a sign change or not, the energy of the function is going to remain the same. Again, if you want to download the notes that I've taken in this video, it will be down in the description below.